I want to now finish up our talk about skew lines, about graphing lines, and also I want to go over the quizzes from the other days. So, lines in 3 dimensions probably will not intersect. If you think about it, you draw a line in space and you draw a second line, it would be really unlikely for it to hit dead on. It's a lot of space for it to miss. But they might, depending on how well set up the problem is. So, skew lines, that's the name for lines that are neither parallel nor intersecting, which cannot happen in 2 dimensions, but it can happen in 3 dimensions. So, here's the equation of 2 lines. X is 1 plus t, y is negative 2 plus 3t, z is 4 minus t. And L2, x is 2s, y is 3 plus s, z is negative 3 plus 4s. I do insist you use different letters for the parameters. I use t in one and s in the other. And that basically means that they didn't start at the same time. So when t is 0, s might be 5 or something. And that just makes sense because there are a lot of different ways you can parameterize it. There's no way of knowing if they're starting at the same time, so you might as well use different parameters. Now, how could you possibly know if these things intersect? Well, I'm going to go over and graph this. I've entered the 2 lines here. Here's the first one, here's the second one. I know I said I like to use S for the other one. On the computer, they insist on T most of the time, so just imagine this one has S's instead. Now we can see these 2 lines, and they don't look like they're intersecting, but maybe they do off in the distance. But here's the trick. If we look dead on at one of the axes, like we did before, and we project, so let's see if we can try and blank out the Z. This is hard to do there. Then it looks like maybe down this way off the bottom of the screen, they'll project somewhere. They'll intersect, I meant to say. If I had to blank out Y, well, that looks really good, actually. It looks like they intersect that there. And so if we did that, we could say, well, here is the X and Z. It looks like X is 1, Z is negative 2, and then we just have to check what about the Y's. And then we'd turn side and say, no, the Y's don't match. So this is basically our strategy here, is to project by blanking out one variable, see if we can find the intersection in the other 2 variables, and then check the one we blanked out to see if it matches. So what does that mean in actual practice? Well, I'm going to give it to you in step by step. So, step 1, drop 1 variable. There's a hyphen there. Drop 1 variable. And usually it's going to be X. Doesn't have to, usually it's going to be Z. It doesn't have to be Z. It could be X or Y. But I usually start by dropping Z and solving for X and Y. But if you try to do that and for some reason it doesn't work, it probably means it's a very rare case where dropping the Z doesn't work. And so you'd start over and try with dropping X or Y instead. Step 2. Solve for S and T by setting x1 equals x2 and y1 equals y2. Step 3, plug in S and T to check X and Y are equal. Step 3 is technically not necessary. It's just a way of making sure that your answer for step 2 is right. But once you have a certain S and T, and then make your X and Y's match, then your final step is to plug in to Z. And though if the z's are also equal, if equal, that's the intersection. If not equal, then you say it's skew, meaning they do not intersect. They just sort of go past each other at different angles. All right, so if you like to take screenshots, here is the screenshot for, let's call it check for intersecting versus skew lines. So let's do the example that we were given and show how this works in practice. Okay. So, our problem, we had L1, x was 1 plus t, y was negative 2 plus 3t. We're going to ignore the z. L2, x is 2s, y is 3 plus s. Ignore the z. So we'll set the x equal to here. So it would be 1 plus t equals 2s, because those are both x. So let's write that 1 plus t equals 2s. That's what we got from saying the x is equal. Now, what do we get from saying the y is equal? We get negative 2 plus 3t equals 3 plus s. Okay. Negative 2 plus 3t. Excuse me. Let me fix that. Negative 2 plus 3t equals, I forgot what it said. 3 plus s. Now this is something you should know how to solve from algebra, but if you don't, come by office hours and I'll be glad to go over it with you. I'm going to say, let's solve for t here. T equals 2s minus 1. So the y becomes negative 2 plus 3, 2s minus 1 equals 3 plus s. Let's solve for s. So let's say it's 6s minus 3 equals, I'll move the 2 over here, 5 plus s. So 5s equals 8. And then s equals 8 over 5. And t equals 2x minus 1, so t equals 16 over 5 minus 1 is 11 over 5. Okay, so s is 8 over 5, t is 11 over 5. Now what this basically means is that you started watching these lines at different times. So after 8/5 of a second for s and 11/5 of a second for t is when they should meet. So that is what we suspect the answer is. So now we check it. All right. So for x, x is 1 plus t, which is 16 over 5. 1 plus 11 over 5. And x is 2s, which is 2 times 8 over 5, which is also 16 over 5. Okay, so the x's work. Y is negative 2 plus 3s, 3t. Don't mix up your s and your t at this point. It would be negative 2 plus 3, 11 over 5. That's negative 16 over 5 plus 33 over 5. Why did I say 16? Negative 10 over 5 is 23 over 5. Let's check what the s is. Y is 3 plus s is 15 over 5 plus 8 over 5 is 23 over 5. Okay, the y's match. Okay, so this tells us we haven't done anything wrong. We've done, all our steps are correct. We found the s and the t that makes x and y match. And that's going to be the only one that works for both x and y together. The question is, does it also work for z? So let's plug into z. Z is 4 minus t is 20 over 5 minus 11 over 5 is 9 over 5. That's Z1. Or is it Z2? No, it's Z2. And Z1 is negative 3. Or maybe it's Z. I don't know. I mix up. I might mix up 1 and 2. Negative 3 plus 4s is negative 3 plus 4. 8 over 5 is negative 3 plus 32 over 5 is 17 over 5. Well, those are not equal. 17 over 5 and 9 over 5 are not equal. So therefore, these are skew lines. Okay. So with that out the way, I now want to talk about the quizzes from the other day. And there was a question. These were questions 43 and 45, 43 and 44 in Stewart, if you need to double check them, in section 12.4 on the cross product. So, we were given A dot B is root 3, and we're given A cross B is 1, 2, 2. Or one of those negatives. Let me double check that. No, it's 1, 2, 2. Okay, it probably wouldn't matter. But now we were asked to find the theta between these. Now, when you're asked to find a variable, you need to somehow change the equations to have that variable in it. So we think, what are the two variables, or the two equations for dot product and cross product that involve a theta? Well, A dot B is length of A, length of B, cosine of theta. And A cross B in magnitude is length of A, length of B, sine of theta. A lot of people left off these absolute values on the A cross B, but it wouldn't really make sense otherwise, because A cross B is a vector, and this on the right is a scalar. It's just real numbers. So you have to have length there. So we can say, how do we combine these? And people did a lot of work, a lot of clever ideas, and everyone got there eventually. But here's the quickest way in my mind. A cross B over A dot B, let's just divide them, would be A, B, sine theta, divided by A, B, cosine theta. We know neither A nor B is zero vector because their dot and cross products are non-zero. So these just cross out. So we're left with length of A cross B. You work out length of A cross B would be 1 plus 4 plus 4 is 3. So that's 3 on top. And A dot B is square root of 3. And then you can try to solve this. Figure out what angle has a sine of 3, cosine of root 3. Well, that doesn't work, so let's simplify this a little. That reduces to 1 over root 3. And I'll divide by 2 on top and bottom. So sine of theta is 1/2. Cosine of theta is root 3 over 2. Theta is pi over 3. Or 60 degrees. Their way to do this even quicker is to say absolute value of a cross b over a dot b would be just root 3, because it's 3 over root 3. So root 3 is tan theta. I left them separated because I can't remember the tangent values, but I remember the sine and cosine. But yeah, that's the easiest way to do it in my mind, just divide it out. But if you solve for length of a or something and then plugged in, you'd end up at the same place. All right, now let's do 44. This one was a little trickier, required getting pretty creative at times. And like I said, it required some ideas of linear algebra that we, strictly speaking, haven't seen, but you can kind of work them out on your own. Or rather, this is the sort of thing that if you're in a linear algebra, you would be expected to do really quick, know how to do really quickly. But we're not, so that's why well, what we have is 1, 2, 1 cross V1, V2, V3. And so that becomes I, J, K, 1, 2, 1, V1, V2, V3 is I, 2, 1, V2, V3 minus J, 1, 1, V1, V3 plus K, 1, 2, V1, V2, which is 2V3 minus V2, I, minus V3 minus V1, J, plus V2 minus 2V1, K. And that equals 3I plus 1J minus 5K. So we have a system of equations here. 2V3 minus V2 equals 3. V1 minus V3 equals 1. V2 minus 2V1 equals negative 5. And so the way to solve this is to pick one variable that you're going to eliminate. So I'm going to say, let's let V3 be the free variable. Because if I try to solve for, whichever one I try to solve for first is not going to work. So let's say, try to solve, how did we do this? So if you say 2V3 equals 3 plus V2, and V1, or V3 equals V1 minus 1, so then we would plug that in, we would get 2V1 minus 2 equals 3 plus V2. And then we take the V2 here and plug that in. We get 2V1 minus 2 equals 3 plus 2V1 minus 5. So 2V1 minus 2 equals 2V1 minus 2. Well, that's trivial. So, okay, so I end up solving for V1 first. So V1 is the free variable instead. It really doesn't matter. You just solve for one of them. Whichever one you get free there, you just declare it. Point is that when we try to solve this, one of the variables is going to end up trivial like that. So we have to make it a free variable. So if V1 is free, well, what's V2? Well, we look at this bottom equation. V2 is 2V1 minus 5. And V3, if we solve it, V3 is V1 minus 1. Well, that's a vector then. V1 can be anything. 2v1 minus 5 is the y, and v1 minus 1 is the z. Now, if you'd solve for v3 first, it would be different. Yeah, the v3 one was 1 plus v3, 2v3 minus 3, and v3. v2, I don't have that one in front of me, but it was like b plus a over 5 or so. I can't remember. But it would be, you'd work it out the same way. Well, maybe we could just work it out from this. You just solve v2 is... Now you have to solve it out. I don't want to do that. Yeah, to solve for v3 and v1 in that case and plug it in there. Well, let's do that real quick. Just for completeness sake. v2v3 equals 3 plus v2. So v3 is 3 plus v2 over 2. So 3 plus v2 over 2. And what's v1? Well, v1 is v3 plus 1, which is 3 plus v2 over 2 plus 2 over 2. So that'll be 5 plus v2 over 2. So these are three different ways of writing what is going to turn out to be the same line. And there's lots of different ways. What we'll discover as we talk more about lines is that there's usually lots of different ways to parameterize them. But any one of these is acceptable. You just basically pick one variable to be free. And this works because there are infinitely many of them. And you just solve for the other two that way. So this is more complicated than what you would have to do on a test. I wouldn't give you a question like this on a test. I basically wanted you to just play around with this for a while and come to understand how the lines work and how they're connected. But what we're saying here really is that when we cross two vectors, we get a third vector parallel to or perpendicular to their plane. And so this ended up being, or rather it was a vector crossed with a second vector that ends up along a certain third vector, and it just defined a line. Now some people ask, could we just get one solution, then use all the scalar multiples? And the answer is no, because that would only work if the vector went through the origin, and this line does not go through the origin. If you plug in 0 for one of the variables, the others are not 0. So it's off of the origin, so therefore you need a different equation for the line. Now the second question was, if we have, what was it? Let me see, I have it right here. Yeah, we had the same 1, 2, 1 cross V equals 3, 1, 5. I want to show none of there are no solutions to this one. Now, if you did this the exact same way as before, you would eventually get to a non-answer like 2 equals 5. And when you get nonsense like that, you know it's going to be no solution. But there is a quicker way to show it that some people thought of that I hadn't even thought of myself, which is, if this is U cross V equals W, then we know W is perpendicular to U and V. So if this equation is possible, then it must be that this first vector is perpendicular to this third one. And the quick way to check perpendicular is do the dot product. 1, 2, 1 dot 3, 1, 5 is 3 plus 2 plus 5 is 10, which is not 0. Whereas with the earlier example, when it was negative 5, you put negative 5 here, you will get minus 5 would be 0. So those were perpendicular. That's why the first one worked and the second didn't. All right. Thank you.